This video is only on one thing, which is the motor principle, which relates back the current in a conductor, which is flowing, in the presence of a magnetic field. Now we'll assume that the magnetic field is uniform. So when you're just learning this, the first concept that you should be aware of is that there is an actual force which is going to be present on the conductor, so on the actual wire itself, if it is experiencing a current flow through it while there is a magnetic field present. So the motor principle states the following, and I take this, okay, from the reference on the physics kind of 11 on the Nelson book. A current carrying conductor that cuts across external magnetic field lines experiences a force perpendicular to both the magnetic field and the direction of the electric current. And we can figure out the exact direction of this force. So I am going to introduce you to here, so to a three-dimensional kind of a vector field that you see here of the magnetic field, that is the blue one, which is being carried through. And it is along the y-axis, but it's moving along in this direction, okay, as you can see there. And then I have an actual conductor, and we'll assume that there is a current which is flowing through this conductor. So notice this is in the x direction in here, and I designated it with a red arrow. And the magnetic field is in this direction. And now you can see there, so my right hand, and we're going to be using the right hand rule. Now I use the right hand rule in this case a little bit different than sometimes what might be shown through other teachers. So this I have learned way back in engineering, and I kind of stuck to it because I really like it. And now that I'm running these videos for grade 11 or foundational physics students, I still try to use this exact same concept of finding out where the force is, and the force is going to be in the direction of the thumb. But first, let's try to break this down and understand what is exactly happening. So if you imagine that you would have a permanent magnet, and let's say you have two magnets. Now it doesn't have to be a permanent magnet. It could be an electromagnetic, okay, magnet which is formed. Yeah, so it does not matter which one you have, but let's assume that we do have an actual permanent magnet. So in a permanent magnet, so if we would have, so on this end, okay, so of the side, and let's say that this was on the north, and this end, so we had a permanent magnet on here, and this was south. And if you would know, so we would have a magnetic field which is going to be flowing in this direction, right? So that magnetic field would be flowing in that direction. Now assume that you have an actual conductor, so a wire, and you have current which is flowing, so this is the traditional current, which is flowing in this direction. Now if we do that, so within here, so you can imagine that, I'm going to just take this for the moment, so let's say that this is the direction of the magnetic field, and this is the direction, so that at least the way that it's shown, okay, within here. And this is of course kind of coming in, so this is three-dimensional. So this would have been your current, and this right here is your magnetic field vector. Now these are vectors, so they do have a direction that you have. And that's exactly what you're seeing here. So you can imagine that, you know, we have one of these, and then we have one of these. So this one is your current, and this one right here is your magnetic field. And now the question is that what happens to this wire if a current is going to flow through it? Well, what's going to happen if you do have a presence of a magnetic field, then there's going to be a force that's going to be present on the wire, and it's going to be pushing, right, or pulling, whatever you like to call it, on that wire. Now, in which direction will that happen? So that actually follows through the right-hand rule. So the right-hand rule states that if you take, and this is the way that I use the right-hand rule, so if you take your right hand and you take your fingers, okay, And your fingers right here, so these fingers are going to be in the direction of the current that you're going, right? So that's where the current is going. So within here, so if I would draw or pretend to draw this, all right, so this would have been, you know, my fingers that are going to be holding up like this, all right? So here's my hand, all right? So my hand. So this is going in the direction of the current. And now what you do is you take that hand and you curl it on the angle which is created with the magnetic field. So it starts to curl in this way. And then the direction of your thumb is going to be the direction that the force is going to be pushing onto the wire, right? So upwards. So within here, so as you can see here, so my hand, okay, so if this is, right, so this is the direction, okay, that you had, and this is the direction, okay, this is the direction of the magnetic field, and I am curling this in that direction. So I am creating an angle which is going from the current, right? So this is going to create an angle right there. And that angle is going to be in the direction. So this is where you're curling, right? So this is what you're going to be curling with. So these fingers from your right hand are going to curl onto. So it goes from the current onto the magnetic field. That's what you would have. And therefore, so when you do that, the direction of your thumb, so in this case, so that direction of the thumb is upwards. So what that is telling us is that your force, so on this particular wire, is going to be upwards, right? So this would have been the force which is going to be pushing this, okay, upwards. Now, you might ask the question, okay, what magnitude? So what is the size of that particular force? So you can find that out, and that typically, okay, gets pushed into, okay, your grade 12 once you start learning, okay, about cross products and then actually what the magnitudes are and how to actually find them out. But for this video, my interest is to let you know this motor principle, which will relate it to motors later on. Okay, and we will use that, okay, so that we can create a motor which is going to be rotating through, okay, and you'll see that there's a very neat way to do it. But for the moment, you just want to be able to understand that if there is a conductor which is carrying a current and it is in a presence of a magnetic field, that magnetic field might be coming from permanent magnets or it might be from electromagnets, okay, so it does not matter, but as long as there is a magnetic field. In that instance, there's going to be a force on the wire, and that force we can find out what the direction of it is. It is indeed dependent on the size of the current itself. It is dependent on the size of the magnetic field, okay, as well, and it is dependent on the angle within here. Now, if that angle is not 0 or 180 degrees, so meaning that your two vectors, so your current and your magnetic field, are not collinear, so they're not in the same line, so meaning that what you do not have within there is that your magnetic field and your actual current is going to be exactly in the same field, so collinear. Okay, so it's in the same exact direction or in the opposite direction. So the angle would have been between them either 0 or 180. Under those instances, if the angle in between them would have been 0 degrees or it is 180 degrees, so they're basically in opposite directions, in those two cases, then there is no force present. But in all other instances, there is going to be a force present, and it will depend on the angle itself. Okay, so and what happens? The biggest angle happens when this is 90 degrees and they're actually perpendicular to each other already. So these are at 90 degrees. Now, if you go back and you now think about this right-hand rule and what it means to you, so if you have these, okay, notice that this vector, so the force, is perpendicular, right, to the two vectors. And that's exactly what the motor principle states. It says that if you do have a conductor which is carrying a current, then the magnetic field, okay, across an external magnetic field, then the force is going to be perpendicular to it. So the force can either be upwards or it can be downwards, right? Because those are the only two that would be perpendicular. So at 90 degrees to both of those two vectors. So they has to be now three-dimensional. Now the question arises, all right, so is it upwards or is it downwards? And we can actually utilize the right hand to help us with the actual thumb pointing where the force is. So let's try this and try to figure out, okay, so in which direction would the force be present, right? So in this case, it was in the Z direction over here, where it creates a 90 degree. Okay, so that creates a 90 degree with this, and it creates a 90 degree with this. And this would have been your force. And it is dependent on the magnitude of your current. It is dependent on the magnitude of the actual magnetic field as well. And it is dependent on this angle that you have. So please remember, if the angle is 0 or 180, then there is no force. All right. Other than that, you will experience some force, okay, which is going to be present. In this direction, okay, it will be upwards. So let's take a look. So what would happen? So if you now take, okay, so now let's say that we have these situations. So here's several examples of where you can illustrate this. Now, by the way, so I have used kind of Desmos, the three-dimensional. So this is the schematic that I've used, and also over here, okay, so I've used to plot it on Desmos, and I can put up a link, okay, in the description below to Desmos as well. So here it is. Let's imagine that we have a current. Okay, so we have a conductor, and this conductor is coming out of the page. Right, so please recall, so this dot means that it's coming out of the page. Now, what does that mean? That means that this right here, it would have been like coming out of the page. So it's moving in this direction, all right? Where you have your dot, so this is moving in that direction. That's what happens here. Now you have a south pole and a north pole. Now, again, it does not matter if this is a permanent magnet or if it's an electromagnet, as long as it creates a magnetic field. Now, if this was not here at all, then we know that, the magnetic field lines would have been going in this direction, meaning from north to south. Now, of course, if there's a current in here, so we also know that when you do have a current, you're creating a magnetic field around it. So this would actually kind of skim over, okay, like this, okay, so as it goes through. Now, for that, I'll put up a link up above there if you want to study how that magnetic field looks like. Our interest is to try to figure out which direction is the force going to be present. Okay, so within here. So what we have is this. So we know that our current is flowing in this direction. All right. So this is where our current flows, out of the page. Now, by looking at this, so as you're going through, we know that the magnetic field is pointing from here to there. So it basically is going in this direction, upwards, right? So that's what we have. So I'm going to just draw it out. So now we have this, okay? So it is pointing now upwards like this. So now you have to take your right hand, and now as you take your right hand, you have to now curl your fingers, okay, towards from the current, so this is our current, onto the magnetic field, all right, so onto the magnetic field, and your thumb is going to be now pointing you in the correct direction. So if you do that, right, so take your fingers, okay, place them in the direction of the current, and now curl your fingers towards the magnetic field. And what you're going to find is that your force would be present in this direction. that's where your force would have been present. So your force would have been pushing you in that direction. So what that means is that this wire that you have in here would have been getting pushed, okay, onto that side because it is present in an external magnetic field. Now, what about the second one? Okay, so within here. So what this means it's going into the page. So in 3 dimensions, what this is referring to is that, okay, so into the page, so that means it's going backwards, okay, like this, okay, so 3 dimensions, so that's how it would look like, into the page. Again, we still have if there was no current, okay, and no wire there, so our magnetic field would have been going in this direction, right? So again, so this means that it's going upwards. So this is still presence upwards, that's the magnetic field. And now again, you take your hand, okay, and you take it in the direction of your current, and then you curl your fingers onto the magnetic field. And if you do that with your right hand, then what's going to happen is it's going to curl in this direction, right? It's going to curl in this direction, and therefore the force is going to be in the opposite, okay? So right there. So that's how it would look like over here. So if you were drawing it, so the force would have been pushing it in this direction over here. That would have been the force, so it's pushing it to the right, if I can draw this arrow. So it's pushing it to the right in this direction. And here it is pushing it to the left. All right, so make sure that you do understand how that came about. All right, so that's these 2 examples that we have. Now, what about the third one? So here's another example so that you can take and see how it works. So in this direction, now we have, so our current, okay, is going to the right, okay, so it's moving in that direction. So I'm going to draw it out. So it's like going in this direction, so in the direction of the Y. Now again, so because I have the north at the bottom and south, so that means, you know, this is still going to be upwards in this direction. And now once again, so now it's going from the current and it curls in this way, right? So those are how your fingers should be curling. Now, if you do that, what is going to happen is that your force is going to be pushing on the wire out of the page. So in this direction, that's where your force is going to be pushing, right? It's perpendicular to both of those. So what that means is that this particular wire, so it's going to be, okay, coming out of the page, all right? So that's the force which is going to be present on that wire, right? So it's going to be coming out of the page. That's the force that we have. Here's the last example, right? So this is the current going in the opposite direction. So now the current is moving in this direction, right there. Again, so my magnetic field, okay, so it's going from north to south, right? So this is what we have. And now what we're going to do is we're going to take this, okay, and we're going to curl our angle from the current side, okay, onto the magnetic field. And if you do that, then that means that your force is going to be now, okay, it's going to be into the page, not out of the page. So it's moving backwards. So notice that the previous one was out of the page. This one is onto the page. So we would have the force, which is going to be present on all of these, okay, points on the actual wire and trying to push it in that direction. So there you have it. So that is the concept, okay, with the right hand rule and understanding what happens to a wire if it has a current passing through it in the presence of an external magnetic field. And you should know which direction would the force work. Now, please remember, so to summarize, if the angle is 0 or 180 in between, then there is no force at all, okay? And your actual force is going to be dependent on the size of the current. So the bigger the current, the bigger the force. The bigger the magnetic field, the bigger the force. And then be careful with the angle. So the angle actually at 90 degrees provides the maximum. All right. Thanks for watching. We'll see you in a future video. Bye, everybody.